Okay, so this lecture is Introduction to the Piezoelectric Metamaterial. In this lecture, we will discuss these topics. What is a metamaterial? Conceptual hierarchy from natural metamaterial to metamaterial. What is the piezoelectric metamaterial? Need for the piezoelectric metamaterial. How to design piezoelectric metamaterials, and of course the applications. So, basically metamaterial is a composite structure only. So, as we know, in the composite structure we have two main parts. One is say reinforcement and second is matrix. In case of metamaterial, this reinforcement actually is equivalent to the meta-atomic meta-atoms, or we can say inclusion, or sometimes unit cell. So, basically these unit cells are designed in such a way that we can formulate the property of our material according to our requirement. And the host matrix, or say host medium or matrix, actually is the same as in case of composite structure. Basically this matrix just supports to the meta atoms. So, basically if you would see this meta, meaning of the meta actually is beyond. So, meta means beyond. So, in the metamaterials means the properties which are beyond in the existing natural materials. That is, if you want to determine, if you want to develop a material that has not the property in the natural material, then we can use the metamaterial. So, the natural materials, as you are already aware of, that is pure substance and say mixtures, and of course these are the again different classifications. This, as engineers, we are already aware of about these different materials. So, basically these materials, so called natural materials, have the properties based on the chemical constituents. What chemical constituents are in the material, based on that the property depends. But suppose sometime we need unusual properties that are not available in the natural materials, then we can use the metamaterial. Now, the example of unusual properties like negative effective mass density. Suppose we want to have say density say negative, right. So, actually density cannot be negative, right. If you have a material, you must be having some density, but this can be possible in case of metamaterial. Similarly, negative stiffness, we cannot have negative stiffness in the usual materials or natural materials, but we can have this in the metamaterials. Band pass, basically a range of frequencies we can allow and range of frequency we can stop. So, that can be possible with the help of metamaterials. Negative refractions, cloaking. So, actually there are so many applications, so many of unusual properties that are required. Now, see in this course, so-called Gyan course. That is something about the piezoelectric. So basically, with the help of piezoelectric materials, we can have tunable properties. So we have the options. We can make piezoelectric metamaterial. We can make some other type of metamaterial. For example, we can make metamaterials aluminum metamaterial, say copper metamaterial, and so on. We want to make piezoelectric metamaterial. In that case, we can control or we can tune the properties according to our wish, right? So that is the advantage of piezoelectric metamaterial. So actually these are very high level demandable, that is piezoelectric metamaterials. So if you would see again, the concept, how we make the metamaterial. So you can see actually generally we have the atoms, right? And actually these atoms are bonded to make the material. So we have the natural material. This is, it may be aluminum, it may be copper, and so on. Now, this material actually can be used to form a shape. That shape may be triangular. It may be a hollow triangular shape. And actually then we can arrange this actually material, right, in the form of the triangular form in matrix. So you can see we have this, this so-called meta atom, right? This is a meta atom. Meta atom actually is a specific shape that is given to the base material, right? And actually we can have this in a, as you can see, this actually is in the periodic order, right? In a sequence. So actually it is not only we can have this, even we can have, say, I want to.
Okay, so that's the right side.
Okay. Yes. Okay. Yeah. So actually, see, this is a hollow triangle. We can actually make even a solid triangle, right? Or even we can make, say, this type of shape, or we can make, say, this type of shape, and accordingly we can have arrangement in this matrix. Suppose you have, say, a square shape. So we can actually arrange this meta atoms in a periodic fashion, right? So you can see actually we have so many combinations, right? We have actually, this is say aluminum material.
There is the instructions, there is no need for buttons, and when you will change the slide, please click on this.
Yeah. So see, though we have only one type of natural material, and actually we can make so many type of materials, so-called metamaterials. And the interesting thing actually is this, whatever shape you are giving to this so-called meta atom, you will be having the different properties here, right? The property of the meta material depends majorly on the shape of this meta atom, right? So actually that is the main concept of metamaterial, right? So again, what we have now, say, atoms, and we know that atoms are actually bonded to make the materials. We have the material, and then actually we can give a shape, a specific shape, or we can design a special architecture of this to make the meta-atom, right? And then actually we will be having what that is matrix and the meta-atom. This combination of matrix and meta-atom actually is known as a metamaterial, right? Yes. So that is the concept of you can see here. Suppose we have this matrix, right? And then we have the meta atoms, right? So the property of metamaterial, that is this metamaterial actually is, depends on the property of bulk material, also called metamaterial, right? So actually we have property of matrix and we have property of meta-atom. Actually we can determine the overall property of the metamaterial, right? So this actually is the metamaterial. So the difference between the traditional and metamaterial composites, as I have told in the beginning, that metamaterials actually are the composites, but actually they have some difference with the traditional composite materials. How they differs, you can see the traditionals, for example, traditional fiber reinforced composite, but they have atoms, then material phase, and then we can have laminate, of course, for the structural purpose. So actually fibers are real materials, right? If you would see in case of metamaterial composite or metamaterial composite, actually again we have the atoms, right? And then we can make a material, right? And actually what we have a special shape, that is the meta-atoms, right? And so these meta-atoms are arranged in the periodic fashion. So fibers are real materials in case of traditional composite, but in case of metamaterial composite, these meta-atoms actually are artificial atoms, because that we are designing according to our requirement. So you can see properties of the traditional composite material depends or can be determined with the help of rule of mixture, load transfer, interface bonding, and actually this you know already aware of this formula to determine the property of traditional composite material. However, in case of metamaterial composite, the properties comes from geometry of meta atom, whether it is a triangular, whether it is a square, or so on, and the periodicity, that is periodic fashion, whether they have arranged in periodic fashion or not, and then actually resonance. So whether resonance is happening or not. So these are the three properties actually that decides the dispersion. So we can say dispersion, or we can say these three properties, right? So basically the property of metamaterial depends on geometry, periodicity, resonance, or we can say combine these three like in the dispersion, right? So the interesting thing actually is in case of metamaterial is we have E effective and we have, for example, say density, say rho effective. That is, these properties depends on the frequency, right? As you can see, this is a function of frequency omega. So basically metamaterials composites are designed to sustain the dynamic loading, right? because under the dynamic loading only we have the frequency, that is the structure can vibrate under the dynamic loading. So, we have the frequency omega. If suppose you have a structure, for example, you have a cantilever beam, I think my laptop should be here. Okay, so you can suppose this is a cantilever beam. If you apply a load say F, suppose this load say is static load or a constant load, right? Then this metamaterial actually is just as a traditional composite material, because in that case we do not have any omega. The structure cannot vibrate, and hence omega is 0. So, this actually E effective is equal to this and this are the same, that is the property you have in case of metamaterial, you have the same in case of traditional composite material, right. So, when we say we have a dynamic load, and as a mechanical engineer we all are aware of the vibrations. Actually vibrations occurs because of the dynamic load only, right. Similarly, if you would see in case of electrical engineering, we have electromagnetic waves, right. So, we have electromagnetic waves, we have vibration waves, we have sound waves, we have even heat waves, right. If you have say heat actually has fluctuations or transient heat, then you will be having the fluctuation in the heat, and we can say heat waves. So, wherever we have the waves, we can use metamaterial, right. So, actually as I told in the beginning that the density cannot be 0, right, the Poisson ratio cannot be 0. However, they can be 0, they can be even in negative, right, if your structure is vibrating, right. So, at a certain instant they may be 0 or they may be negative, but as such in the real sense they are not actually negative or they are not 0, right. So, that actually is very important concept of the metamaterial. Metamaterial actually are designed only to sustain the dynamic loading, because dynamic loading actually has the frequency, and the effective properties of the metamaterials depends on the frequency. Hence, you can see what makes metamaterial different from the ordinary materials like natural materials. So, in case of natural materials, what we have properties because of the atomic bonding, chemical compositions, and these properties actually are static, they cannot vary, right, and they are fixed by the nature. Examples you can see in modulus, density and permittivity. In case of metamaterial, what we have properties comes from the geometry, periodicity, resonance, and these properties are frequency dependent.
Buttons are not required to.
Yes. So, therefore, metamaterials are not defined by what they are made of, but by how waves propagate through them. Now, classification of metamaterials. So, classification of metamaterials may be they can have many bases to classify. One of course may be a physical domain, like electromagnetic domain, acoustic domain, mechanical domain, thermal domain, even biology domain, chemical domain, and so on. But actually in the mechanical engineering or say even civil aerospace, generally we generally deals on these 4 domains, and therefore actually I have on these 4 domains. However, the domains can be extended. So you can see in case of electromagnetic domain, but we have the wave, light wave or radio wave, and the properties which we have interest to design or to modify to suit our requirement actually are permittivity and permeability, right? And you can see applications, we can have invisibility cloaks, that is using the SLAT technology, that actually is very demandable nowadays. And acoustic domain it may be. So here we have the waves, sound wave, even vibration waves. And here actually we have interest to design or to modify the density and say or modulus that actually are used in the sonic crystal, right? Or in case of say submarines, and actually we have the submarine, in the sea. We want that there should not be any noise that should come outside. Right? Everything should be in silence way. So for that we can design the material of the submarine of the acoustic, of course, metamaterial acoustic. Mechanical domain, we have elastic wave, right? And we have interest in determining say stiffness, or even we can have other mechanical properties, right? Then thermal domain, heat waves are heat, and we have interest, for example, conductivity and so on. So actually that is only one way of classification of metamaterial. We have actually other domains as well. For example, classification by wave control mechanism. So as we have seen that is the metamaterials actually are designed for dynamic loading. That is to control the dynamic loading. That is to control the waves, right? Because when we have dynamic loading, we have the vibration waves, we have sound waves, we have thermal waves and so on. So we don't want that there should be any vibrations, we don't want that there should be any waves. So in that case, we can actually classify the metamaterials based on the Bragg scattering metamaterials, and second one is locally resonant metamaterials. The Bragg scattering metamaterials actually are because of periodicity in the metamaterial. That is, you have seen already that meta atoms are arranged in the periodic fashion. So actually it can be proved mathematically that if we have a structure that has periodicity, so we can control the waves, or we can stops the waves. Of course, there may be some range of the frequency, but frequency range can be stopped. So we will discuss this actually how it can be. So this actually can be done only if we have the size A. A actually is the lattice size, that is the distance you can see here. This actually is A means the size of the atomic unit. Actually D is the distance or say lattice size. So D actually is the distance between the two meta units or meta atoms. Actually A is the size of one meta atom. So the Bragg scattering phenomenon actually happens when we have a is equal to half of the wavelength. Wavelength of the wave, the wavelength of the sound wave, the wavelength of the vibration wave, and so on, right? So actually this has a characteristics. You can say this is because A is equal to lambda by 2. So it can be only, that can be done only for high frequency band gaps, or the waves which we have the high frequency that can be stopped. So basically limitations are we have the ineffective at low frequency. When we have low frequencies waves, then we cannot use the Bragg scattering concept. Then we do use locally resonant metamaterials, and the locally resonant metamaterial example actually is the piezoelectric material. So in that case, we have to have the size of piezoelectric meta atom less than, very less than the wavelength of the wave, and this actually concept is used extensively in case of aerospace, and of course in the mechanical engineering for the structures that have that are designed for the low frequency domain. The classification of effective metamaterial behavior. So basically how the metamaterials are behaves. So actually this is not just depends on the property whether metamaterials has negative density or say stiffness negative, bulk modulus negative, and poisonous negative, and so on, right? Extreme property metamaterial. Now actually you can see this is very interesting. We have ultra light yet stiff. So say rho actually is almost 0, ultralight means rho is equal to 0, and the stiff K actually is very high, stiffness is high, but usually it is not possible, right? See, when we have density, in fact density and actually K are proportional, right? If you see the relations. So actually if you have rho high, then you also have the K high. But in case of metamaterial, we can have this reverse trend. We can have rho 0 and we can actually have K according to our requirement, right? Similarly, we have ultra compliant yet strong, right? So you can see examples: architected lattice materials and say mechanical clocks. Classifications by adaptability. So that we have passive metamaterials and active metamaterials. So actually in case of passive metamaterials, properties we cannot change. Suppose say we have this, we say this rho is equal to 0, for example. Then we cannot again change this when the system actually is under the operation. However, in case of active metamaterial, we can actually change rho according to our requirement. Though we had made metamaterials, but still we can change when the system actually is operating. For example, in case of piezoelectric material, right? Because the piezoelectric materials actually can be tuned with the help of external voltage, right? So you see actually this we have so much interesting applications of the metamaterials, and then you will see in the future that everything may be made of metamaterial. Of course, I am saying this statement in very hype sense, but this actually is my understanding, because the future actually demands the properties of the structure or the system that can be designed according to our requirement. But if that property are not possible in the natural metamaterial, so we have to have design, or we have to have use the metamaterial. Now, the actual topic of this course, so-called piezoelectric metamaterials. So what we have, the piezoelectric metamaterial actually we have see meta atom. So these are the meta atoms, right? So these meta atoms are made of the piezoelectric materials, and this we have the matrix, right? So matrix, of course, you can see actually these atoms are arranged in the periodic manner, right? And if you want to have, that is active property, then you have to have also use every metatom with the shunt circuit. That is, will be having resistance, inductance, and of course capacitor actually is piezoelectric metal itself. As you know that piezoelectric metals behaves as a capacitor. So we have capacitor, inductor, and resistance. So we actually have the shunt circuit. So it is just like in case of vibrations, but we have when we have vibrations waves, right? Suppose we have the vibrations and hence vibration waves. So because of that, this piezoelectric materials actually will be having energy. That energy can be changed in the heat energy with the help of this RC circuit, right? So in this way we can actually control the vibrations. I think those are working or those are aware of piezoelectric materials, they may be aware of this smart structure where we have sensor, actuator, and controller. So basically what it is just like when sense the vibrations and then apply the force by the actuator on the structure. So this force is applied by an external source, so called electric battery, right? So actually sensor sense the vibrations, but to apply the force on the structure we need to have a battery to supply the voltage to the again actuator, so called piezoelectric actuator. But see in this case, in case of metamaterial piezoelectric smart structure, we do not need any controller, or we do not need any actuator, we do not need any battery. It is coming here and then actually automatically it is dissipating into the heat energy, and of course the actual vibrations are going to be damped out, right? So in case of piezoelectric, traditional piezoelectric smart structure, we do need actually controller for every purpose. But here we can avoid a controller, even we can avoid actually electric battery, right? But of course, if you want to make more smart, then you need to have no controller, right? So you can see what we have. The piezoelectric metamaterials actually are the periodic structure with piezoelectric inclusions or piezoelectric metaatoms coupled to the electrical circuit, so called shunt. Every metaatom is connected to the electrical circuit, then creates tunable band gaps and adaptable property. Tunable band gaps means if we want that this much the vibrations of this frequency actually should not be there, right? So we can tune. See, vibrations of a certain frequencies will not come in the structure. The vibrations of other frequencies may be there. So if we have this type of provision in our structure, that is known as the tunable band gaps and adaptive properties. Of course, we can change the stiffness, right? So we can change stiffness or other this piezoelectric coefficients, right? So piezoelectric transducers embedded to the structure and connected to an electrical circuit to dissipate vibrational energy as heat or store it electrically, right? So I think you would also be aware of this energy harvesting, right? So if you don't want that this energy should be dissipated into the environment, actually we can store this energy, and that would be energy harvesting, right? The piezoelectric shunt circuit offer a passive or semi-active approach to damping vibrations by leveraging the electromechanical properties of piezoelectric materials. So in case of piezoelectric materials, you already aware of, we have coupling between, say mechanical field, electrical field, and thermal field, right? I think this already have discussed, so I will not go into so much detail. Generally, this coupling actually with thermal can be ignored because this thermal coupling actually gives the pyroelectric effect. Pyroelectric effect actually is not so much in comparison of direct piezoelectric effect, so that may be even ignored. So sometimes actually we can ignore this. So this part can be ignored of these equations, and of course this can be used equations for the piezoelectric domain. That is, we have so-called stress, right? T is stress, C is the elastic modulus, S is a strain, E is the piezoelectric coefficient matrix, capital E is electric field, and D is the charge per unit area, right? And again E, S and B, actually E small v is the permittivity. So now, interestingly, actually the piezoelectric material actually comes under 3 domains. Like you have seen, in case we have seen electromagnetic and mechanical, acoustic and thermal, right? Of course, there are many more. But the piezoelectric actually metamaterials are actually the interface between these 3 domains: acoustic, mechanical and electromagnetic metamaterials, right? How it is, that actually you can see from this picture, right? Of course, you are already aware of this with this discussion. Yes. So need for the piezoelectric metamaterials. So the need for the piezoelectric metamaterials arises from the demand for lightweight, tunable and intelligent system capable of controlling waves rather than just responding to the force, right? Piezoelectric metamaterials are needed to transform piezoelectric structure from local actuator into the wave controlling metamaterials, right? So basically traditional piezoelectric materials actually are the local actuator. So you can see again the difference. We have conventional or traditional piezoelectric structure and metamaterial piezoelectric structure, but we have the control. In case local, we have distributed, because so you can see this figure. Actually, this figure is so-called conventional piezoelectric structure, and this is now based on the metamaterial. So we have band gap. There is no band gap. That is, we cannot actually remove range of frequency, but here we can have tunability limited. We can have high, low frequency control, and excellent. So actually you can see here. See, in case of aerospace, to control the vibration of aircraft structure, or even say in the satellite antenna, where we have very low frequencies vibrations, people have suggested to use this piezoelectric actuator, traditional piezoelectric actuator, and of course they have also demonstrated, but they have limitations, and therefore now it would be better if they will use the piezoelectric metamaterial. Excuse me. Now, type of piezoelectric metamaterials. Passive piezoelectric metamaterials. Excuse me. So basically, here we have based on the shunt circuit, we can classify this. So we have RLC. If there is no any outside control on this, then it is passive. If we have controller as well, then it is active. Sometimes we can also make programmable piezoelectric metamaterials, so controlled via embedded microcontroller or software defined circuits. So actually this is some advanced level, so we should not say, for example, worry about this at the moment. Now, how to design a piezoelectric metamaterial? So you can see the component of piezoelectric metamaterials. That is, we have the unit cell, right? we have the host structure, so called matrix, right? And then we have the electrical shunt. Then we have the dispersion relation actually, that I will let you know what are those. So these three things, first unit cell, host structure and electrical shunt. So basically unit cell means designing this patch, right? Of course the shape, excuse me, whether it should be say square, it may be having triangular shape, or even you can as you wish. So basically when we say this piezoelectric metamaterials, then they also have this electromechanical coupling. So we have this charge. So these equations which I have wrote here, actually that are for 3D, right? And these equations, the first equation actually is direct piezoelectric equation. It is Q Cp V theta U, that actually is for one dimensional case. So we can convert equation number, this equation, second equation, right, into simplest form for one dimensional. Q is equal to Cp V. Cp actually is capacitance, V is the electric voltage, theta is the strain charge coupling, and U is the relative displacement between the piezoelectric material and the host, so called matrix. Of course, if it is completely embedded, then it is same as of, displacement of U is displacement of the host. So we have this much, these simple equations. Of course, we can integrate this. So we can take differentiation to determine the current. Current actually is rate of charge. So then designing of unit cell means sizing, giving the sizing to the unit cell, and of course shape. So sizing means the A should be very small than lambda. So we should be aware of what is lambda, right? Lambda of course depends on the requirement, which type of vibrations we have. Then patch spacing, that is how much distance between the two patches, so called distance D, right? So D actually includes both A plus gap. Then the host structure, we have the actual host structure depends on wave type. If you have longitudinal wave, then we can use rod. If we have flexural wave, then we can use beam or plate. If we have lamp wave, then we can use plates again. Baseline, of course, sometimes we can also use shell. The baseline dispersion, so basically this is dispersion means actually is the relationship between frequency and wave number, and this actually decides this is decided based on the thickness, stiffness and boundary conditions to place the natural mode near the intended band gaps. So we will discuss this in the second lecture. Then modeling of abstractions, but we can use this beam theory or Midlin theory, plate theory, right? Or Timoshenko beam theory in case of Bundy, and in case of 2D Midlin plate theory. So of course, as you can see, this is very complicated structure. So we cannot use simply with the conventional way. We have to use numerical method, so called finite element method. So generally we do use finite element method to design the host structure, right? Then the designing of shunt. So we have RLC, right? So sometimes actually we have only resistance, we do not have L, right? So in this case actually we have only there is no sharp band gaps, just it is used to damp the vibrations. Inductive RLC, so we can have this actually is very well known equations. Then we have negative capacitance when we actually have capacitance negative. So actually this can be done with the help of a tunable band gaps. So design guidelines actually choose shunt based on frequency range of interest, that is whether you have to use R or you have to use RLC or whether you have to use negative capacitance, right? Passive and active requirement, then stability considerations. Now the dispersion relations, as I mentioned that dispersion relation actually is the relationship between frequency and wave number, right? So we should be having a detailed idea about this relation, that is what are the frequencies that are stopped because of the periodicity, and what are the frequencies which we want to again stop with the help of say resonance, for example with the help of piezoelectric material. So in case of you can say actually this simple structure, this is one dimensional monoatomic chain, or actually we can assume just like a simple rod that is made of spring and mass, right? So what we have mass, that is spring, mass and spring. So we can assume that a rod is made of many number of spring and mass. So actually we can see the response of one of the mass and spring, and actually that will give you an idea of complete spring and mass, and hence the complete wave, right? Because actually wave will be flowing inside this medium. So we can actually have the relationship between this accelerations and the damping, and of course the deformations of one at one point. So we will do this. Actually, we will be having this relations. Like this actually omega is this is the ratio of omega and omega naught, right? And if you would see in this case, if we have only 10 masses or 10 springs, so this is actually the range where the waves is passing, or I would say the frequencies at which the system will vibrate, these 10 masses will vibrate, or these are the 10 modes, and more frequency actually are not having any effects on the system. So see, this actually is my stop band, this is my open band. Similarly, you can see here this actually wave is flowing up to this 2 hertz, up to this 2 hertz, and there is no frequency actually, there is no waves that actually is passing through this. So we can say wave motion, or we can say vibrations of the system actually can we have similarity. So we will discuss actually this how this expression came. This figure we will discuss in detail in our next lecture. Now different applications. So what we have, applications of piezoelectric, application of metamaterial piezoelectric metamaterial is vibration control, for the vibration control. So actually we can have adaptive vibration suppressions in beams and plates. So you can see this is my beam, and we can have both sides, that is metamaterial, piezoelectric metamaterials, and of course every side will be having the RC circuit. So actually when we will be having the vibrations, it will convert into the heat waves. Shell and panel structures. So in aerospace and underwater vehicles, like in submarines, piezoelectric metamaterial cells will, with shunted resonant circuits, achieve low frequency vibration control, which is difficult with conventional materials. So examples in this are in the aerospace, vibration suppression in fuselage panels and morphing wings. In civil engineering, seismic vibration mitigations in building foundations. In robotics, we can use vibration isolated joints for precision motion, and in marine structures, suppression of shell vibrations in the submarines. Similarly, the applications of piezoelectric metamaterials in sound control. So, piezoelectric metamaterials suppress noise by preventing sound waves from propagating, not by absorbing them, right. So, that actually is the main concept. So, here the noise actually or sounds is not absorbed, right. This is the waves actually are cancelled out, right. How they are cancelled out, that we will discuss. So, see the low frequency sound by absorbations. So, digitally controlled piezoelectric metamaterials can achieve high efficiency absorbations in the low frequency range, where conventional materials are ineffective. Adaptive acoustic panels. Array of piezo patches connected to tunable shunt circuits act as resonant absorbers, allowing engineers to shift absorbations band in the real time. Underwater noise suppressions. So, piezoelectric metamaterials embedded in plates shell are used to attenuate underwater acoustic waves. So, again in the applications further in automotive cabin noise reductions in the lightweight panels. Aerospace, suppression of fuselages and cabin noise. Civil engineering, noise barriers for urban environments. And marine underwater noise suppression for stealth and environmental protections. See, traditionally actually piezoelectric materials are used to control the vibrations or suppress the vibrations for thin structures. But recent applications are showing that even they can use for thicker structure as well. Of course, that would be piezoelectric metamaterial. For example, people have used to control the vibrations of turbine blade. You see, actually turbine blade is not thin, and they have shown successfully that this metamaterial, of course, piezoelectric metamaterials can be used for this purpose. Energy harvesting applications of the piezoelectric. So, in the field of energy harvesting, the primary challenge is that ambient vibrations are often low frequency and they are actually randomly distributed. For example, in the traditional piezoelectric materials, they have this problem because they do not behave properly on the low vibrations, and again actually these vibrations are randomly. So, for this purpose, the piezoelectric metamaterials are very suitable. So, conventional piezoelectric harvesters are narrow band resonators. If the vibrations frequency shifts slightly, power output drops significantly. Piezoelectric metamaterials solve this by using structural architecture to trap. That is, we can have this meta atoms, right. So, we design these meta atoms in such a way that they can work on the smallest frequencies. So, concentrate and down convert mechanical energy. Now, structural health monitoring. Piezoelectric metamaterials embedded in breeze or aircraft panels harvest ambient vibration energy to power wireless sensor. So, as you know that nowadays there is a smart city concept. So, a typical smart city will be having million number of sensors. So, to power the sensors actually is a challenge, because though they do not need so much energy for the operation, but they are many in numbers. So, that problem can be solved with the help of piezoelectric metamaterials. Cell powered aerospace skins. Aircraft fuselage panels with periodic piezo array harvest vibrations energy during flight. provides distributed power for embedded monitoring systems. So this power can be used for the monitoring purpose. The smart city infrastructures, building foundations or railway track equipped with piezo metamaterials harvest seismic or traffic induced vibrations, and this energy can be used for lighting, monitoring, or Internet of technology devices. And of course, portable electronics, we have piezo metamaterials layers in shoes or wear harvest working vibrations, and that can be used for powering small electronic devices. So see, actually there are many applications for this. So as there was image about piezoelectric materials that they have low output. This piezoelectric metamaterials can overcome this, right? So it's a matter of how you are designing, and they will work accordingly. So see, actually this field, so-called piezoelectric metamaterials, is very interesting. People have proposed these applications, and they all are under the research phase at the moment. In the development phase, it may take some time, but once it will work, then you will see things will be very easy. So this is our first lecture. If you have any question, please let me know. Yes, any question?